And good evening, everyone, and welcome to the very first live session for the first course. Before we begin, I assume that you have watched all the videos. Any queries regarding that part?
Yes, I have some doubts regarding the bandit problems.
Okay, okay.
Yeah, so the explore exploit dilemma that the bandits follow,
Mhm.
I couldn't understand it properly.
Okay, okay. Sure, sure. So, explore exploit is okay. The multi-arm bandit is like an abstraction to uh, represent this explore exploitation diagram. So in a particular situation, you there are multiple options available, and you pick a hand. Basically, you pick an action and take that action, and you receive a reward corresponding to that. Okay.
Yeah,
So multiple actions have different rewards associated, different reward distribution associated with each of the action or each of the hand. All
hmm
right.
yes,
So you can consider the slot machine is like abstraction. So you consider that every time you pull a hand, you get a reward, either 5 rupees, 10 rupees, or 100 rupees.
yes,
So there are multiple hands. By pulling each one of them, you get some kind of reward. So some arm has, let's say, 5 rupee average return. Another has 10 rupee, 20 rupee, and so on. So let's say you get a chance to play with such kind of multi-arm mandate. What will be your objective? What will,
to get the maximum amount from that slot machine.
correct, absolutely right. And in order to do that, you need to figure out the arm with the best expected reward. Is that correct?
Hmm. Yes.
Right. Now, you in the beginning, you when you have 5 arms in front of you, and you don't know which arm has what expected reward associated with it. What will you do?
We'll try out like the bandits one by one and see like which one gives bigger reward more frequently or something like that.
Absolutely right. Yeah, that's the exploit dilemmas. Right. So let's say you pick first arm, all right,
Hmm.
and you don't explore at all. Imagine this situation: you receive 5 rupees. Next time 4 rupees. Next time 6 rupees, and keep pulling that arm, and you never
Hmm.
explore. It might be possible that there are arms which with expected reward 100 rupees.
Okay.
Okay. Then in this situation, do you think it is okay to just pick one arm and keep pulling it?
No, no,
Right.
no.
So
Yeah.
right. So you have to try out other arms also.
Yes. So
So
that's the
exploration,
explore part. Uh,
that is true. That's true.
okay.
Now the exploitation part comes in. Of course, you want to explore, but you don't want to keep exploring for a very long time. You want to have some algorithm with which with certain confidence, you can say, okay, this is my arm that after so many experimentations, after so many times I pulled different arms and I recorded the rewards I received. With proper algorithm, I can say, okay, this is my optimal arm, and I want to keep pulling this one, right?
Mm-hmm.
So you let's say you got the optimal arm after certain uh, pulls that this second arm it gives me 100 rupees expected reward, and all others are giving me lesser than that. So once you figure that out, you just want to keep doing that, right?
Okay.
Right. So this is the of course if you know from the beginning which arm is going to give you the best expected reward, you will just keep pulling it and
Yeah.
don't
Right.
explore any of arm, right?
Hmm.
But since we don't know that, we want to explore a little bit, and at the same time, we don't want to explore without any bound. We also want to, maximize our reward also, which is your expected reward. So once I find out the best app, I want to keep pulling.
Yeah.
Does this make sense?
Yeah. Yeah.
Okay. Any other questions before we begin? I think we can start with the practice questions. But before that, any questions from any of the videos? So I'm assuming that all of you have watched the first week's videos. Is that a correct assumption?
Yeah, mostly. Uh,
Okay. Cycling, I would strongly advise that, not just for this week, but every other week also you watch the videos first. Otherwise, then if you watch the videos following the practice assignment and discussion would be much easier.
Yeah, yeah, sure. Like it was scheduled for today. I joined.
Okay, okay, sure. All right. So if there are no further questions, let me pull out the practice questions and then we'll start going through them one by one.
Sir, I have a question regarding the course.
Sure.
Can you please give you some more details on the programming assignments that we're gonna get?
Right. So the programming assignment. So what in what respect do you want?
So, like, uh, do we have to apply the whole like uh, like do we have to train a model like an agent or something, or like they will be just like how we were given assignments in MLP and such subjects where we have to apply
No,
specific functions or like that?
no, you will be asked. See, the assignments you can expect to definitely train certain agents in given some environment. That is definitely there. Second, you can expect to be asked to apply certain algorithm in order to train that agent.
Okay, okay. And we'll get these assignments from week 3 onwards because week 2 has no assignments.
Uh, okay, I'll check into this and come back to you. I
Okay,
don't
sir.
recall exactly
Okay.
which week the program assignments is.
Okay, sir.
Sure. Apologies for the interruption.
Sir, we are going to do practice assignments, right? Because I have a question. Question number 1.
Yeah, we are going to do the practice assignments. Okay. So question number 1 asks, which of the following can be solved with reinforcement learning? I think this is from lecture 1, where Randall said is talking about how reinforcement learning is different from supervised and unsupervised learning. Let's look at the examples. Learn to identify which ones have dogs and which ones have cats by looking at the set of images and corresponding curriculum inputs.
So my question is that
Yeah.
like
Okay.
there are papers and there are programs where we can use reinforcement learning to do image classification.
Reinforcement learning for image classification. Okay.
Yeah, I can send a link using like two state queue learning. I don't get the meaning, but like there are things.
I see. I see. See, so this particular question doesn't expect you to, pick a particular technique in reinforcement learning and see whether whether it can be used as a supervised learning or not. It's a general. So see, even though it is okay, I'll have to take a look at the papers how they are using Q learning as well as what objective they are fulfilling. But this particular question doesn't expect you to go into that detail. It's a general question about understanding of reinforcement learning. It's a difference from supervised and unsupervised learning.
Okay. Sir. Okay. It was not included in the correct answers. That's why.
Okay. So option number 1. What kind of learning problem is this?
That's supervised learning, right?
Right. It's a supervised learning problem because you have certain set of samples and set of labels. The labels are cats and dogs, and the samples contain the images. So first cannot be the option. Second, learn to write a cycle.
Yeah, that's an RL because we are not
That's
like supervising it, anything. We're just leaving it
right.
to do it itself.
Right. Learn to select the most relevant news articles on a website's front page.
That's also RL. Sir gave us an example of Yahoo News in the lecture.
That is the,
But I mean, without RL also we can achieve that, right?
of course. So, like recommendation systems or
Yeah.
self-supervised learning algorithms can be used to solve this problem. But
Mhm.
RL sits on top of all of this.
Yeah, I mean, given there is a feedback implemented, then it can be implemented, right?
Yes.
Okay. And time series, I guess.
Sure. Predict the price of a stock for next week. You're looking at last month's performance. It's like regression problem.
Forecasting, right? It's like under that
Sorry?
umbrella. It comes under forecasting, right?
So I didn't hear you clearly.
Yeah. So for next 5 days, prediction comes under forecasting set of problems where we take general forecasting algorithms. So they are not part of RL.
So is it only me who's not able to hear him clearly, or others also?
No, he's saying that these set of problems come under forecasting.
Forecast. I see. Yes. You're right. They are not. Arbitrary. Now let's go to question number 2. So which of the following is not a useful way to approach a standard multi-armed bandit problem? Assume bandits are stationary. So when we say bandits are stationary, this means that the reward distribution for each of the bandit is stationary. It's not changing over time. So first step option is, how can I ensure the best option is the one which is mostly selected as the time tends to infinity? Okay, second option is, how can I ensure total regret as time tends to infinity is limited? How can I ensure an arm which has an expected reward within certain threshold of the optimal arm is chosen with probability above a certain threshold? And last, so third one is indicates a PAC. The fourth one is, how can I ensure that when given any two arms, I can select the arm with a higher expected return with a probability above a certain threshold?
So is the first one, is it?
So fourth
So-
one.
Is the least useful?
Okay, so it is asking for
Not a useful approach.
not a useful way to approach a standard MAB problem. So first, I can ensure the best action is the one which is mostly selected as time to suit. So it is like a good description of a MAB problem, because I want to find out the optimal arm, and once I do that, I just keep pulling this. So as time increases, I want to increase the number of times I have selected the optimal arms, and ideally, that's the only arm I select after a certain point. What do you say?
That would mean you're just exploiting, right? No exploring at all. In fact,
That
you
is
may
true.
not.
Right. See, so the ensuring part, how can I ensure the best arm is golden, many times or mostly as time tends to infinity, it internally indicates that there is some exploration needed. Because without exploration, you cannot find the optimal.
Okay, so you mean that since it is saying that best action is already included in the words,
Yeah.
it means we have finished exploration, is it?
Either
Or
exploration,
either finished exploration, or we are pretty confident that okay, this is optimal.
True. Or we are going to explore if we are starting from the beginning. Point number 2, how can I ensure the total regret as time tends to infinity is minimal? That is also an objective that introduces, in the middle of the week or slightly later half of the week, that regret minimization, there are regret minimization algorithms also, and we want to do that, right? We want to minimize the regret. So we want to increase our expected reward. So this one also seems to be relevant. The next one, any questions so far? At any point of time you have any questions, just link or raise your hand. Point number 3 is, how can I ensure an arm which has an expected reward within a certain threshold of the optimal arm is chosen with probability above a certain threshold?
So this you're saying corresponds to PAC, is it?
Yes.
Okay.
So it says that, how can I ensure an arm which has an expected reward within a certain threshold of the optimal arm? So optimal arm is mu star, and the arm that I'm choosing is, let's say, mu star minus epsilon.
So this is not a correct answer, right? Then
This is also not a correct answer, because this is an
it's
accepted.
actually a good strategy, yes.
Yes, it's actually good stuff. So we're left with the fourth option. How can I ensure that when given any two arms, I can select the arm with a higher expected return with the probability above a certain threshold? Well,
But that is also a good idea, right? Like it says given any two arms, which means eventually you'll find the best arm.
that is true. That is true. But that's not the overall objective of the problem. I just want the optimal arm. I don't want to keep exploring the unoptimal or non-promising arms.
Okay.
Is that so? Imagine that there are 5 arms, and I think by chance I pick 2 very poor arms, or any 2 arms, even if one of them is optimal. I have to, then in the next step, what will I do? I'll pick another 2 arms.
Pick another 2 arms, yeah.
Right. So let's say there are 4 arms. I pick 1 or 2, and I figure out which one is better. Center exploration. Then I have 3 and 4 also. So either I pick 1 and 3, or 1 or 4, and 3 or 4, and keep repeating this experiment. So basically, it's like a binary search.
Yeah.
But
Yeah.
it's going to consume a lot many steps or lot many pulls than it is required, because the other algorithms which are study later, they just as soon as they find out that, for example, UCB, as soon as it is confident that this particular arm is not going to it's not going to give me promising rewards, it never explores it, right?
Hmm.
So this is not the correct way to approach. Any questions so far? All right. Let's go to point number 3. Credit assignment problem. So question number 3. Credit assignment problem is the issue of assigning a correct mapping of rewards accumulated to the actions that led to them. Which of the following is the reason for the credit assignment problem? So point number 1 says rewards. Okay. Is this the issue? Is this the problem? Point number 2 is rewards are delayed. So rewards are delayed in the RL setting.
Not
Agent
always, but if they are, then this is correct.
True. Okay. Agent cannot observe the reward. If that is the case, then credit assignment is absolutely useless. Next is RL agents do not face credit assignment problem. They do. So 3 and 4 are absolutely wrong. Rewards are restricted to the scalar value. No, that is not the idea of credit assignment. The main idea is this one. Rewards are delayed in the RL cells. So if you remember the examples I took in the lectures, which was about tic-tac-toe and Minis, for example. So Minis also does some kind of credit assignment, but very poor version of credit assignment. But it also does that. And so Ritter also comes, for example, he talks about TD learning. Probably this is coming in second. So yeah, the correct answer is rewards are delayed in the RL setting.
But the third also seems correct, right? In fact, the third and the second one are, to me, they seem equivalent. Rewards are getting delayed because the agent cannot observe the reward at any given time. It may observe them at the end of the game, for example. Like in the tic-tac-toe example. So the above could be true because of the third option also.
See, the third option is how I interpret this option. The agent is incapable of observing the reward, or he never gets to operate.
Even when the experiment is finished, you mean?
Yes.
Okay. Then makes sense.
So agent actually observes the rewards, and at the end of episode or continuous setting in the experiment, but definitely he receives the reward, and based on the reward, once it receives the reward, it goes back to its previous states and actions and assigns in a manner so that it tends to repeat the winning actions. So if it cannot observe the reward, there is no way for it to learn.
Okay. So that means that for multi-arm bandits, there will be no credit assignment, right? Like that won't apply for multi-arm bandits?
For multi-arm bandits, yeah, multi-arm bandits is a special case of full RL problem where the sequence is not there. Whatever the state in which you start, whatever action you take,
When
you
there's
end up in
only
the
one
same
action before getting the reward.
There's only one action.
Okay.
Question number 4. We're trying different algorithms to find the optimal R for multi-arm bandit. Plot the expected payoff versus time for each algorithm for which the expected payoff satisfies some function with respect to time. Which of the following functions will have the least regret? Know that the optimal expected payoff is 1.
Planets.
Yeah, if you plot them, that's the option. Okay, so just to revise the grid a little bit, I'm going to draw a chart. Right. Is my screen visible?
Yes, no.
Do you see any kind of flicker? No issues, right, on the screen?
No.
Okay. 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 So I'm drawing very roughly, and so let's say this is your line for 1. Okay. The expected average, and you start from time 0, and this is the kind of curve you get. Okay. So this is, let's say this is region number 1, and this is region number 2. So which one do you think is the correct? 1. That is correct. So see, every time you get lesser reward than the optimal one, lesser reward than the reward you get from doing the optimal one. The difference is our regret for that particular action, for that particular instance or custom. So when we do this experiment, or when we are doing this experiment again, when we are trying to find out the optimal. Every time we don't pull the optimal, whatever the difference, it's my regret, and over the time it accumulates. So region number 1 is actually here. Question number 5. Consider the following statements for the epsilon greedy approach, assuming the reward is restriction. First option, always keeping epsilon constant is a good approach. Option number 2, or statement number 2, large values of epsilon will lead to unnecessary exploration in the model. Statement number 3, pulling down epsilon too fast is problematic as it cannot guarantee correctness in value estimates.
I think only 2, right?
Okay. So large values of epsilon will lead to unnecessary exploration in that is correct. That is correct. Yeah, what we want to do is when we have as we increase the number of samples from multi-arm bandit, we definitely want to decrease the slowly decrease the epsilon so that it
1 is
converges.
definitely wrong. Yeah.
Yes.
1 is definitely wrong. 2 is definitely right. Third, do we is there such a thing as cooling down? Because I thought there is that other temperature parameter. This may be a trick
Right.
question.
No, it's not a trick question. So you can interpret cooling down as decreasing.
Oh, okay, okay. Yes, then 3.2 is fine
Yes, 2 and
because
3
it
are-
reduces exploration.
Right, right. So what the point number 3 is, if you are decreasing exploration too fast, it is possible that we might miss the optimal value.
So
So
the
it's-
last option then, yes.
2 and 3 go back. Question number 6. What are 2 ways of defining the probability of selecting an arm in Solomon plots? Select the option regarding price choice. So the first one, what it does is the probability of taking particular action A is the estimate of that action divided by sum of the estimates of all the actions. And the second one is you actually take e raised to the power estimate of that particular arm and average it over with the estimates of all the arms, given that they have been raised to the power. So it's a standard softmax formula. So now we have 4 options. One is better choice, it requires less complex computation. Second option is better choice, as it can also deal with negative values. Third is both are good, as both formulas can found probability in range of 1. Fourth one is better, as it can differentiate well between close values of QTA.
What is the question? I mean, could you scroll?
Sure. So which one of these is better way to choose the probability estimate?
I'm not sure about barrel, but I mean, with a regular softmax, I mean, it can handle negative value, but summation might not.
Yeah, I think the second one is clearly, well, first of all, it is softmax, and then the first one is not, I mean, there is no guarantee that that will actually result in a probability at all.
That is true. That is true.
But I'm wondering
Yes.
if option number 2 is the correct explanation for that. Yes, it does deal with negative values. And since it's an MCQ, I guess, yes, that's the right answer then.
Yes. The second option is the correct. So by raising any quantity e to the power any quantity, any real number, is always going to be 0 or more. It can never be negative. Since we are computing probabilities, that is any probability that we do. So the second option is that first is definitely not correct. Both of those formulas can be gone. No, third one is also incorrect. It's better. It can differentiate well between the close values of 2 3 units. No, actually, it's the fourth one is also incorrect. If it were the other way around, for example, option number 2 can differentiate well between close values of QT. That would have been correct. So, only this sense. Question number 7. What are the objectives of a multi-arm pattern problem? Identify the optimal arc dimension. Is that correct?
Yes.
Yeah,
I'm not
true.
sure about the word eventually, but you
Right.
definitely have to find the optimal arm in some reasonable time. Now, even
Right.
what you mean by well, let's leave that aside for now.
Option 2, maybe, lower the conflict.
Right. So, Jaidev, I agree with you. Theoretically, eventually is okay, but practically, we need it. We have some budget of pulling the number of times we can pull the arms.
I think maybe option
Yeah.
1 and 2 combining, they make the same thing.
What do you mean
no,
by complexity of the number of samples?
Right. So the algorithms that that sir has covered in the lectures, they do not directly give you numbers. I mean, so the number of times we we need to pull the arms,
Hmm.
it is bounded by some complexity, some expression. So it's so if you are familiar with asymptotic complexities
Oh,
and
you mean okay, the
big O,
in the greedy epsilon graphs, the upper limit, you mean? Is that what you mean? Oh no, sorry,
that
that
is
is the upper bound of the payoff, not of the number
Right.
of samples. Okay, yeah.
right. So that is asymptotic. Yeah, you got the point that epsilon greedy, the payoff graph does incorporate the asymptotic concept. I'm talking about, for example, simple examples. If we take what is the time complexity of quicksort?
Okay. It should not take n squared order of n squared samples to figure something out.
Right. So, in the similar fashion, sir also mentions in the regret optimization problems that the number of circles drawn is has the upper bound of O of something. Right. So that's the idea of
Yes, in that
complexity of
case,
number of
this is the
circles.
correct answer, and the other three are clearly wrong.
So this is correct. Maximize the number of times the suboptimal arm is chosen. Why do we want to
No,
maximize?
why would
this?
you want to do that?
Right. Identify the optimal arm immediately. That is also not.
It's not possible.
Yeah, it's also possible immediately.
But I mean, yeah, good question. Is it can it be posed as an objective?
But exploration will be affected, right?
Yes.
There will be no exploration at all.
Last option, there is no need to maximize the average reward over the time. Then we need the purpose of doing this.
I mean, yeah, why do this?
Solving the problem.
Absurd.
Yeah. Question number 8. Which of the following best refers to PSA optimality solution to bandit problems? Okay. So epsilon is the difference between the reward of the chosen arm and the true optimal arm. Delta is the probability that chosen arm is not optimal. N is the number of steps to reach PSA optimality.
The third one.
Okay. So let's
I
go.
think it is the third one because
Okay. Let's go
epsilon
to
is
the-
something you cannot minimize. Number of steps. PAC doesn't say anything about minimizing number of steps itself. Right? Does it?
Number of steps. No, it doesn't ask. It is not an. So PAC is not. I think any. What should I say? It is trying to optimize something. What it is trying to say is, if this is the error that this is the expected error. I mean, you're happy with epsilon. An arm which differs with the optimal arm by epsilon amount, and there is the probability, or now there are three variables, like epsilon, n, and delta. So delta is saying that the probability of selecting an optimal arm. Suboptimal, right? So 1 minus delta is the probability of choosing the optimal arm. So
Right.
yes, so given epsilon and n, maximize the probability of choosing the optimal arm. This statement seems to be correct. Does this make sense? Any questions regarding this? This is basically the definition of PSA.
Oh, okay, cool.
Sir, but the given answer is first one.
Given delta and epsilon, minimize the number of steps to reach the PSA optimality. You are right.
Sir,
Yeah,
but the
check.
definition itself states PSE means like we have to maximize probability, right?
Yeah, let me check on this one. I think it's a straightforward conclusion from Sir's slide.
Okay.
Question number 9. Which of the following is true of the UCB algorithm? The action with the highest Q value is chosen at every iteration. After very large number of iterations, the confidence intervals of unselected actions will not change much. The true expected value of an action always lies within its estimated confidence interval. With a small probability epsilon, we select a random action to ensure adequate exploration of the action space. Okay, so in case you have watched the videos, it will be pretty straightforward. But in case you have not, so I'll give you a very quick overview of it. So UCB is upper confidence bounds algorithm. So every time it pulls an arm, it keeps track of the confidence interval for that particular arm.
The second one is correct, right?
Let's so the action with the highest Q value is chosen at every iteration. Is this correct?
No, because like we try to balance exploration and exploitation by considering both the estimated value and its confidence interval.
That is correct. After a very large number of iterations, the confidence intervals of unselected actions will not change much. It seems to be correct because the formula for selecting a particular arm is it maximizes QA plus square root of 2 of log n divided by n of a. So number of times that particular action has been taken. So yes, after a very large, so it is increasing with respect to n in square root of n. Square root of log n, so it's a very, very small number. So it seems to be correct. The third one is the true expected value of an action always lies within its estimated confidence interval. So it is an assumption.
Yeah, sure, but this is for epsilon greedy exploration strategy, right? Like it will more be fit for that.
The third one.
Yeah, like it states epsilon greedy strategy, right? Where we try to maximize it.
No. We are talking about confidence interval, right? So in epsilon greedy, we don't take care of confidence interval at all. We just look at the estimates at particular time t, right?
Okay. Right.
Okay. And option number 4 is with a small probability of epsilon, we select the random action to ensure adequate exploration of the action space. So this belongs to epsilon greedy algorithm, not UCB.
Oh, this is what I was referring to. Okay, I thought you were on 4th. Okay, sorry if I was confused.
Right. So I think 2 or 3, one of these two should be correct. Which one of them is mentioned to be correct?
Sir, 2.
Option number 2. This one, see, so sir also mentioned this in the lecture as well, that the interpretation, it's an interpretation that the expected value lies within its estimated confidence interval. But that's not, if you look from a strictly statistical point, that's not the correct interpretation, right? But for the algorithm, we do it. I think that's right. Option number 2 is correct, not the third one.
Okay. Like it does not guarantee, right? That it can happen or it cannot happen, but it does not have a guarantee.
Right. It can lie outside also.
Okay.
Question number 10. Suppose you are in charge of maximizing the revenue of an online advertising company. We need to devise an algorithm to show you relevant customized advertisements out of thousands of millions of visitors. So the number of advertisements is in the order of thousands, and the number of visitors that visit the website every day is in the order of 50. In this context, consider the following. So one assertion is for each visitor, selecting a relevant advertisement can be treated as a multi-arm mandate problem. Reason is different visitors might have different interests and preferences. To customize advertisements for a visitor, an NAB can be done. So we have four options: assertion and reason, both are correct, and reason is actually explaining the assertion. Next is both are true, but they are not correct. Next is assertion is true, reason is false. Next one is both of them are false.
I don't think for as
It's the
optimization of
second one,
revenue,
right?
reason might not be true, right? Because
Okay, so assertion, different visitors might have different interests and preferences to customize advertisement for each. For a visitor, an NAB can be learned. Why not? Why is it not true?
It
I mean,
can be
are
learned,
we
but
are we looking at generated? I mean, click realization as a quantity to optimize, or just a like is that relevance as a quantity to optimize here? I mean, in the question they said revenue should be increased, right?
Okay, right. So in order to increase the revenue, the idea is to so assuming for a minute that these 1,000 visitors are not these thousand advertisements are the only set of advertisements. They don't change. They don't die out, and the visitors are also fixed. These are the same visitors. No new people come in for the sake of simplicity. Okay.
Okay.
Right. So in order to maximizing the revenue of an advertising company, it's very similar to maximizing the expected reward.
Okay. Some available options. Okay. Got it.
Right. Now, the assertion is for each visitor, selecting a relevant advertisement can be treated as a multi-arm problem. So what will happen is the multi-arm bandit, each arm will be an advertisement. And you get my point?
So I'm not sure about the multi-arm bandit. So,
Okay, let's say there are 10 stories, 10 news articles, 10 advertisements basically, and under it, visitors, right? So for first visitor, we can, assuming that we have enough number of samples and all the other things are in our favor, then for a first visitor, I can create a multi-arm, 10-arm bandit problem, 10-arm bandit machine, and the visitor gets to choose, gets to pull one arm at a time, many times. We have enough space. So can we say that I can eventually or theoretically or practically, I can select optimal arm for that visitor? Can I say
yeah,
that?
we can. Yeah.
Right. Now the second visitor comes in. For that visitor, can I also do the same thing? Keep a separate multi-arm bandit for it and train it or not train it, learn the optimal arm for that particular user,
Yeah.
right? And I can do this for all the users,
Hmm.
right? So this is what the assumption is. For each visitor, selecting relevant advertisement. So every advertisement is an arm, can be treated as a multi-arm bandit problem. So it seems to be good. The reason is different visitors might have different interests and preferences. To customize advertisement for a visitor and maybe can be learned. Does it make sense?
Yeah. I mean, for each filter, there is a different. I mean,
Sorry.
sorry. Only each visitor has a different maybe like multi-arm bandit to suggest, right?
Second, your voice is not clear.
No. Second, I mean, for each visitor, there is a particularly separate MAB.
That is correct.
Okay.
We're not talking about how practically it is feasible. However,
Okay.
Theoretically, this is possible given that we have enough number of samples from each user for each story. Okay.
More of an exhaustive search at this point.
I wouldn't say exhaustive. Yeah, you can say that we have more than we require many number of samples.
Yeah.
Yes, so option number one seems to be correct. Any questions?
It's not a question related to this, but in the textbook there is that section on testing this, the epsilon greedy algorithm. I think just it's called the 10 armed bandit test bed or something.
Okay.
And I think Ravi also had mentioned that the charts he had encouraged that should probably try and figure out how to reproduce those.
That is correct.
So what they've done is that you take a 10 arm bandit and assume that each branch, each arm gives a Gaussian, gives a reward which is normally distributed.
Correct.
And the means of all the 10 arms are again randomly selected by default.
That is correct.
All of them have unit variance and blah, 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 some settings there, right?
Mhm.
Now, let's say I start playing this game. And before I start, I have no idea about anything. So my first I have to decide which arm to pull, right?
Yeah, you randomly select an arm.
You randomly select that arm because I don't know anything.
So you
Now-
initialize the estimates to be exactly same.
Yes, and I think there is in the graded assignment or some other. Sorry, it was an exercise in the textbook itself. Where say assume that 0 is the payoff for each arm to begin with,
Okay.
or at basically at time t-1, the payoff is 0, and you start accumulating from there. So you pick the first arm randomly, right?
Right.
Now when I pick it, I get some reward, right?
Correct.
And now my that particular arm has become greedy now because everything else is 0 at
Correct.
t equal to 1.
Correct. That's
Now
it.
what do I do? Do I start becoming greedy from this point itself, or do I wait? Because so the algorithm says that let's say my epsilon is 0.1,
Mhm.
which means that with 1% with 10% probability, I can pick any of the other arms. But 90% of the time, I'll keep picking the first one because that's the only one that has non-zero payoff so far.
Okay, so it is there's one step. If you add it, you are right on the target. So once,
Exactly.
yeah. So once you pick the arm, let's say first arm, and it is not optimal, but it is greater than 0, and now it has become your greedy arm.
Exactly. Yeah.
That's the arm with the best estimate.
Yeah.
Then in the next round, you flip a coin or flip a virtual coin, which
Hmm.
tells you whether you got the whether you have to explore or exploit.
Be greedy or not greedy. Yeah.
Right, right. So based on that,
Hmm.
if it is greedy, you pick the same arm again. If
Hmm.
it is exploration part, then with
Then you pick one of the other arms.
10% probability, you can pick any of the arms, even including the optimal arm estimated so far.
So that is my question. So basically, you start becoming greedy from t equal to 2 onwards. You don't like wait for some time to. Is that correct?
So when you say greedy, it's
Hmm.
epsilon greedy, right? Even in this,
Yeah, that's what I meant. Sorry, epsilon greedy. So that starts the moment you have a single non-zero reward, which
Right.
means t equal to 1.
right?
I see. So it's not like, you give it some warm-up time and after that you start, which is that keep pulling arms randomly until say 5 iterations and then start becoming epsilon greedy. Nothing like that. From the starting itself, you are epsilon greedy.
Right.
Okay, cool. I want to see if that the chart actually makes sense. I mean, the given chart does. I just want to see if this actually works out in a series
Yeah.
of-
So if you write some code to reproduce this experiment, the charts will more likely be very, very similar to what's in the text.
Hmm. One other thing is that again, the fact that each arm has a normally distributed reward, is that just like a convenient assumption, or is this like is there some sort of rhyme and reason to it? Or we are basically saying that every arm will have some distribution of rewards. We don't know which one, but assume that it's Gaussian. Is it like that?
So,
Sorry, I think you broke off.
okay, now audible now.
Yes. Yes.
Okay, so one thing I can very positively say is
Hmm.
that the rewards, maybe the Gaussian distribution may not be the case for every immediate error problem, maybe some other reward distribution, but there is a probability distribution underneath. Okay, so that is one. In real world situation also, when we are trying to solve full error problem, you will come with transition probabilities and so on and so forth. And so the reward, uh, so coming back to immediate error, so the rewards are not constants. If they are constant, there's not much exploration I have to do. You have to just pick one arm, every arm one time.
Got it.
Why?
I guess one way to say this is that the distribution itself has to be learned for each arm
The distribution.
of rewards.
I wouldn't say that we want to learn the distribution. We want to learn the expected reward from that particular arm.
Correct, which means you're anyway learning mu for each one.
Yeah, you're learning new.
And in most cases, I think we can have that simplifying assumption that once you have mu, maybe it just takes. And since we can learn mu, we can also learn sigma.
That is true. However, see, I believe that there is some connection with central limit theorem.
Okay.
It doesn't matter what is the underlying distribution is. For example, if you are talking about UCD, when we are estimating the upper confidence interval for each and every arm. So, if we sample from certain distribution, no matter what the distribution is, it becomes by the virtue of central limit theorem. By sampling from it, we get a normal distribution.
The sum of the rewards will always look like normal.
Correct.
Okay, so that actually answers my question. Then assuming that rewards are normally distributed doesn't harm anything. That's a valid assumption to take.
Okay. Any other questions?
I have a question with respect to GAN
Yes, sir.
given RL. I mean, I'm not sure. I haven't read the literature, but how feasible it is because I mean, I mean, given GANs, I mean, we are expecting some kind of natural output or some kind of objective is available. Then again, reinforcement learning, you need to learn from my bio mistakes. So is that right now? I mean, is that like achievable point, or maybe supervised learning is the way currently they work?
So, Sankrit, I'm not sure I got the question correctly. And the way you are asking, it seems like you are trying to figure out what is the latest state of
No.
JN plus
Mhm. Yeah.
Yeah, I'll have to look at it. It would be great if you can write an email describing the problem that you are trying to solve.
Sure.
Any other questions?
This is not a question really, but a request. Is this time fixed? Like we're going to have exactly 7 every Saturday, 7 to 9,
Yes.
or is it flexible a little bit?
Yeah, so we actually fix this time on the weekend so that most of the people be able to join. Even the working professionals, the Saturdays are off, and in that also they.
Okay, cool.
And one request from me, could you, if possible, could you share the lecture transcripts? I mean, virtually is not updated yet with the transcript.
What is not updated?
Transcripts and lecture transcripts and the slides basically in a supplementary content.
Okay, sure. So lecture plans for the first 2 weeks you are asking for the entire class.
I mean, whatever it's possible and viable or legal. Yeah.
Sure. We'll definitely get you the slides. Sure. The lectures are yeah. So any comments on lectures? Are you? I hope that you are following them back. Sir is describing the topics in very detail. All right then. If there are no further questions, shall we close the session?
Sure. Yeah.
All right. Have a good night, everyone.
Thank you.
Thanks, sir. Bye, sir.
Bye.